This book weighs 1 kilogram and contains about 90 million billion joules of energy. If we consider that humanity used an average power of almost 2,100 gigawatts of electricity in 2010, it means that the energy in this book would be enough to supply electricity to humanity for 11 hours. If I sold this energy, I would earn almost 5 billion euros. I would be rich. How do we know how much energy there is? That's what the famous Einstein equation tells us, E equals mc squared. However, Einstein doesn't tell us where this energy is hidden. It's up to us to find that out, otherwise we'll miss out on those billions of euros I calculated. We'll see where the energy is hidden by trying together to imaginatively extract all the energy given by E equals mc squared from this book, which we'll consider to weigh 1 kilogram. We'll invoke the known laws of atoms, the composition of protons and neutrons, with quarks, gluons, even the Higgs field, in our attempt to release all that energy. Will we succeed? Maestre, start a new episode of the physics lesson. This book weighs 1 kilogram and contains an amount of 90 million billion joules of energy worth $5 billion. How do I know? From Einstein's formula, E equals mc squared. Look here, I multiplied the mass of 1 kilogram by the speed of light squared. Where is this energy hidden? Part of it is hidden in its potential energy. Look, I'm dropping the book on the floor. How much energy is released? The energy is mg. Where m is the mass, g is the gravitational acceleration, and h is the height. We know this from school. At this height, about 1 meter, it results in 10 joules. That's 10 millionths of a billionth of a percent of the maximum energy, so little. If I sell it, I make a millionth of a euro. Yes, you saw that right, my name is the same as the coordinator of this textbook. And yes, I use Wolfram Alpha for calculations. In a way, it's an older version of CGPT. Now let me throw away the book. What speed did it have? I think it was about 5 meters per second. What would be the energy released? It's the kinetic energy, meaning mv squared divided by 2. M is the mass and v is the speed. I get about 12 joules. How much is the potential energy? Very little, man, very little. I better burn the book. Should I burn it? Heat releases some of the energy. How much? Each gram of cellulose paper releases about 4 kilocalories per liter. I put this into Wolfram Alpha, which automatically converts the units for me. And I get that burning it releases 16 million joules. That's 16 megajoules. I would get a few dozen cents if I fully recovered this energy and sold it. Not bad, although this book costs more than that. What if this book were made entirely out of uranium atoms? I mean, if I had a kilogram of uranium enriched to the maximum, how much energy would I get from it and how much would it be worth? The nuclei of uranium-235 isotope are unstable. If a neutron approaches them at a moderate speed, the nucleus splits into pieces which then move at very high speeds. They reach a water reservoir, heat the water which generates steam, and then the steam drives an electric turbine. In other words, in uranium fission, energy is released, which then becomes the kinetic energy of the reaction products, and this energy is then recovered by classical methods. Energy released is calculated with Einstein's formula. As we discussed in the previous lesson, the total mass of the reaction products is less than the sum of the initial masses. In the case of uranium fission, the mass difference in this case is about 0.0788%. However, this would be exactly the energy obtained from fission if we didn't have losses along the way. 0.0788 of the 90 quadrillion joules in this book means about 70 trillion joules, which if I sell, I get about 4 million euros. Hey, I'm in business. Now, a ton of TNT, trinitrotoluene, has an energy of 4 billion joules. That means that 1 kilogram of uranium, which is 70 trillion joules, is equivalent to 20,000 tons of trinitrotoluene. It's no wonder that at the end of World War II and the beginning of the Cold War, the method was used to build atomic bombs. The Hiroshima bomb, for example, was equivalent to 15,000 tons of trinitrotoluene. As you can see, so far I haven't managed to extract even a tiny bit of the energy stored in a kilogram of this. What should I do? Let's say this book, which weighs about a kilogram, was made of hydrogen atoms and I used the fusion method from the sun. How much energy would I get? In the sun, at a temperature of 15 million degrees and pressures of 250 billion atmospheres, the fusion of hydrogen atoms begins. 4 of these eventually form a helium atom. The mass of the helium atom is less than the mass of the 4 initial hydrogen atoms. The mass deficit is 0.1%. The energy we gain through this fusion process from the initial 90 million billion joules of 1 kilogram of hydrogen is also 0.7%, which is 10 times more than with uranium fission. By selling it, I would get about 40 million euros. Well, in practice, it's not that easy. As you know, at ITER in France, a reactor based on fusion is being built. But it's not hydrogen fusion that's being done, it's the fusion of its isotopes, deuterium and tritium. The advantage is fusion doesn't require as much pressure as in the sun. The disadvantage is that hydrogen isotopes are harder to obtain than natural hydrogen. Since the energy released in hydrogen fusion is, just in our example, 10 times greater than that from uranium fission, it's no wonder that the method can also be used for nuclear bombs. That's how hydrogen bombs appeared. So far, we've extracted less than 1% of the energy hidden in a kilogram of matter. Can we do more? Do you know where most of the atom's energy is hidden, the one given by Einstein's formula, E equals mc2? Let's discover together by looking at an atom. The atom is made up of electrons orbiting around the nucleus. With the electron's mass being about 1,000 times smaller than that of the nucleus, it means that the energy from Einstein's formula is somewhere in the nucleus. Let's look into the nucleus. We have protons and neutrons held together by the strong nuclear force. To separate them, we have to overcome the nuclear force, so we use energy, so we don't gain anything. But let's say we use this energy and end up with separated protons and neutrons. Most of the atom's energy is stored in these particles. The majority of the energy is in the protons and neutrons. But how do we get it out? Let's see. We'll take the proton as an example. What is a proton made of? Of 2 up quarks and 1 down quark. And guess what? If we were to open up a proton, we would see how the 3 quarks move at speeds close to the speed of light. And we know, the higher the speed, the greater the kinetic energy. So what we need to do is to release the quarks from the proton. Because they're moving so fast, we take away their kinetic energy, for example, by letting them hit some targets. It's clear. Here we are in the realm of science fiction, a civilization with technology that has evolved for many thousands of years. In addition, there's also a practical problem that's hard to overcome. Free quarks don't exist in nature, so they can't be released so easily from the proton. But hey, why not dream? Let's say we have the technology to release quarks from the proton. How much energy would we release? We need to compare the rest mass of the proton with the sum of the rest masses of the reaction products. We'll have a huge surprise. Thus, the mass of a single quark is much smaller than the mass of the proton. The sum of the masses of the 2 U quarks and 1 D quark that make up the proton is less than 1% of the proton's mass. This tells us that if we release the quarks from the proton, we release 99% of the proton's rest energy, that is, almost all of it. Where was the energy stored in the proton? About half is stored in the kinetic energy of the quarks, which move at speeds close to the speed of light inside the proton. The other half of the energy is stored in the gluon field that surrounds the quarks. Gluons are the particles of the color force that act between quarks. They are kind of like relatives of photons, the particles that make up light. In practice, it is most likely that advanced civilizations will recover the energy of gluons and the kinetic energy of quarks without releasing the quarks from the proton, but through a series of decay reactions that ultimately produce various particles. In the end, this way 99% of the mass of protons and neutrons will be extracted, and therefore of atoms. In the end, let's say that only 1% of the rest mass of the quarks remains. Can we extract that too? Quarks are elementary particles that form protons and neutrons. We could extract energy from them, but that would endanger the entire universe. Currently, the quark is considered an elementary particle with no internal structure. Where does the mass of the quark come from, and therefore the rest energy it has? From the interaction with the Higgs field. That's what the standard model of elementary particles says. The Higgs field fills all space and particles move through it like a spoon in honey. Some of them are slowed down in their movement by this background. This happens for the electron and for the quark. That's what the standard model shows us. Removing this last energy from the quark essentially means making the quark's rest mass zero. That means cancelling the interaction with the Higgs field because that's where the quark gets its rest mass from. How an advanced civilization could completely cancel out the Higgs field? So the quarks would have nothing to interact with to gain rest mass? But be careful. By cancelling the Higgs field in a portion of space, the vacuum as we know it now with the Higgs field would change its properties. For example, in this way, the rest mass of the electrons that happen to be there would also be cancelled. The electrons would become particles without rest mass, which would consequently travel at the speed of light together with the quarks, which would also have lost their rest mass in the process. That would be a disaster. Why? Well, if the electrons traveled at the speed of light, they would escape from the atoms. The atoms would disintegrate in the entire area where the Higgs field was cancelled. The phenomenon is called vacuum decay. Current calculations show that this process could be uncontrollable. That means the vacuum decay could extend to neighboring areas. Basically, it would propagate at a speed equal to that of light. That would, of course, be a disaster in the universe. The vacuum decay would also spread to other areas wherever there are atoms, and there, the masses of quarks and electrons would change. The atoms would also disintegrate along with everything they formed: stars, planets, living beings. So let's hope that if an advanced civilization does something like this, they are careful with what they do. In the end, however, in those areas where the Higgs field no longer exists, the rest energy of the quarks would be zero. They will now travel at the speed of light, just like photons, which also have zero rest mass. How advanced civilizations will recover this last piece of energy from quarks, we do not know, because the standard model of particle physics with everything we know today doesn't say anything about that. However, I have no doubt that advanced civilizations will have found an answer to this last puzzle as well. Until next time, please subscribe if you haven't already by clicking this subscribe button right now. I want to thank those who support us on Patreon and those who become channel members here. I'm Christian Prasura, you are cool, and I wish you all the best. Goodbye.